Hello and welcome to a tutorial on how to use Datrics AI platform to do predictive maintenance modeling. And we're going to be starting with predictive maintenance template that has been already added to the platform. The data we will be looking at was acquired from NASA Prognostic Data Repository, and link to that will be in the description below the video. Let's start the template of the pipeline right away, and in the meantime, we can start looking at the data itself. The data looks like this. We have 100 simulated engines. We have the operation settings of the engines. We have the sensor indicators for those two turbofan engines, and we have the remaining useful life. This is basically how many cycles the engine went before critical failure. And here we have like just the IDs of the cycles. There are also two index columns that will be dropped right away. So the potential problem with this data set is we don't really know where something is starting. So for example, if we are looking on amount of cycles and remaining useful life, we see that for this specific engine, it lasted for around 155 cycles. If we would look at some other, let's say 92, we would see that the engine actually lasted for more than twice as long. So just looking at the amount of cycles itself is not enough. So we built two different models that are being averaged in the end, and provide us with around like 90% accuracy to estimate on when the engine is about to reach a critical point. So here we see that if we plot the absolutely same stuff, so time in cycles and remaining useful life, we can see that this engine actually failed at iteration 341, and as you remember, the previous one failed in 155. So just using the amount of cycles is not enough. Let's look at what the results of this are. So if we look at the cycle count, we look at these three sensor data because they are the most important for the model, and we can also see the end of life prediction tag. So you see that the model is actually catching end of life indicators quite nicely, and we are sure that using this model to figure out if failure point is imminent is going to provide you with good data-driven solutions. Let's look at the pipeline itself in more detail. So the very first thing we did here is upload the data set. You can use this specific data set from our samples, or you can either press plus and upload your own data set, or you can connect the database and use the data from there. The next thing we do is just drop the index columns, because the models would just simply remember which index corresponds to which failure indication, and that is not what we actually want. The next thing we do is we do a missing values treatment. We see that 6 sensors actually have missing values, and we just drop those because they will not provide us with any like meaningful data. Then we do the split. So we split the data into 2 separate data sets to train the model, and then to evaluate how well the model performs. We take first 90 turbofan engines to train the data, and here we will take one of the remaining engines to validate how well the model performs. So this is a small brick that allows us to understand, allows us to calculate what actually we're trying to predict. Remaining useful life is just the amount of cycles that the engine is going to go through before the imminent failure point. We are trying to understand if it's a time to replace the engine because there are less than 20 cycles left. The one hot encoding and filter columns are used here to transform Boolean variables into integers, and those are just better for the models. We are using two different models here. One of them is the binary model, where we're basically trying to understand what is the probability that the engine is going to fail. The other model we're using here is the regression model, where we are trying to predict how many cycles the engine has left on it. And after that, here you can see that we are doing the exactly same thing. We are trying to understand if engine is predicted to fail within next 20 cycles. The next thing we do is just combine two data sets together. We average two models out, do some basic renames for having the column names more understandable, and then feed that to the dashboard that we can use to look how actually the model performs. Oh, and one more thing I forgot to mention is we are actually normalizing the sensors from here. So how these sensors were selected, if we look at the models, we can see that there are basically importance features for what actually contributes to the model's precision. And we see that sensors 7, 9, and 14 are contributing the most. Since they are at a very different scale, we can actually see that. Let's look here. We can see that here. So for example, sensor 7 is around 550, sensor 9 is around 9,000, and sensor 14 is around 8,000. So if we would plot those together on the same plot, we would not see like the minute deviations within each sensor data. So to tackle that, we are actually normalizing the columns. Basically, we're just squashing them together to deviate around 0.5. And yeah, let's look on how that looks. So we're going to plot against the amount of cycles. We're going to look at these three sensors, and you can see that if we actually remove the lines, like as time passes, the sensors are starting to deviate from their normal-ish distributions. What actually we can do here is, this is the end of life prediction flag. So basically we can plot on when the model thinks the engine is about to fail. And we can see that like the basically first signs appear around 40. Yeah, actually that's around 30 cycles before the failure. Like the actual failure points, I would say around 320, like the indicators, and that is roughly within 20 cycles of the failure. And like once we reach the higher cycle count, the model just shows like everything in red. The other thing we actually can look at in the same dashboard is if we plot the actual end of life indicator versus the prediction. So we can see that through 200 almost 300 cycles, the model predicts that everything is okay with the engine. And here we can see that the deviations from that are starting to appear roughly 30 cycles from the failure point, and model reaches like almost 100% for the first time at 12 iterations before the failure, and at 8 iterations before the failure, the model is constantly like reaching zero. So I would say this model actually can be smoothed out a bit, but the predictions are very reasonable, and this can be treated as a good baseline model for the predictions and for providing the decision maker with some good data, like actually data derived approaches. So I believe this is it. The things I think you can play with is first of all looking here and trying to understand what might suit you better, because the number 20 was taken quite arbitrary. Maybe number 10 or number 50 would make more sense for your specific use case. So this is the very first thing I would try to look like. Also try visualizing your data and trying to understand when actually it's quite reasonable to take the cutoff point. The other thing that I potentially would consider you might tweak is the columns you are displaying here. So if you remember, we went to train model and look at the performance to understand which sensors are having the biggest impact on the model precision. So here we have 7, 9, and 14, and those are the sensors that were normalized and then visualized on the dashboard. You might want to change these to some that match your specific use case a bit more. Feel free to utilize this template, tweak it, look at the visualizations, and if you have any questions or comments, we will be happy to answer those. Thank you.